2.6 talks about implicit differentiation. Up till now, every problem we had, every problem that we took a derivative of, we had y equal. They all look like that. So when we take a derivative, we didn't really ask much. All what we did, we took it for granted. What we did was we took d dx at both sides. Since the x doesn't match y, we picked dy dx. That became like the norm. Since this matches, we bring the power down, subtract 1 from the power, everybody's happy. So that's what we've been doing up till now. Now, I'd like to look at a problem, same exact problem. What if I would have moved the x squared to the left? Now if I say take a derivative, well, derivative of the left side, derivative of the right side, derivative of 0 is 0. The left side. When I glance at this, I'm not used to seeing a y and x. I'm used to seeing y equal. Well, if it's not there, every time I take a derivative and what I'm differentiating with respect to doesn't match, I pick a d dx of that. Since this matches, this is my traditional derivative. And of course, I could add 2x to both sides and I get the same answer. It doesn't make sense for you to do an operation, get one answer, and do it by solving or moving an equation, such as what we just did, and get a different answer. What if I move the y to the right? Well, if I take a derivative, again, of both sides with respect to x, because that's what we're doing. Well, derivative of a constant is 0. Now when I take a derivative of this, the negative you ignore when you differentiate. Since the x doesn't match the y, I'll pick a d dx of that y, plus, since this matches, just a traditional derivative, move that over, and there it is. And if I look at the last example, now I change the problem. If I want to take a derivative of both sides, well, derivative of x, since that matches, that's a 1. Derivative of y squared, well, before I reach the y, this is a power function. Based on the chain rule, I'm going to bring the power down, subtract 1 from the power, times the derivative of the inside, since that doesn't match. And in this case, even if I don't want to simplify, I must solve for dy dx. So dy dx would be 1 divided by 2y. So it's not traditional to see a derivative of y and y in the same problem, but that does happen, and it's going to happen soon. Let me give you another approach of getting this implicit differentiation business out of the way. If I was looking at taking a derivative with respect to x, d dx of y, that's dy dx, derivative with respect to x, I would bring the power down, subtract 1 from the power, times the derivative of the insidemost function, which is a cosine of x. Done. If I was to look at the next example, take a derivative, well, it's still a y cubed. If I take a d dx of y, you bring the power down, subtract 1 from the power, kind of what we just did right there. And then times the derivative of the inside, which is secant squared of x. And if I was to look at a polynomial function, d dx of y, which is dy dx, you bring the power down, so it's kind of the same process for all of these three. Times the derivative of the inside, which is 4x cubed plus 2. Now comes the tricky part. So, if I was to tell you what did you do, you would say, well, I took a derivative of the same kind of function. It's a cubic function. One time, the composite function or the embedded function was a sine. One time, it was a tangent, and one time it was x to the fourth plus 2x plus 1. If y is a function of x, and I say take d dx, you would say dy dx equals, bring the power down, subtract 1 from the power like we did on these three, times what? Times the derivative of the inside. What's the derivative of the inside? D dx of whatever that is. Now, u, okay, this is not registering at all. U could be in part E a sine, it could be in part F a tangent, or it could be in part G an x to the fourth plus 2x plus 1. If I didn't tell you what it is, you say, okay, you know what? The derivative will be 3 times whatever you choose u to be, times the derivative of u, which is pretty much what we did on each of those. That's implicit differentiation. Whenever I take a derivative, and what I'm taking the derivative with respect to doesn't match the variable, you pick a derivative of that. So, starting with I, and again, I'm finding d dx of all of those. Well, that doesn't match, but it's a power function. You bring the power down, subtract 1 from the power, times, like we did. I don't know what y equal. Y could be a sine, y could be a cosine. Whatever it is, take a derivative of that. Here I need the product rule. Derivative of the first is a 1 because it matches, times the second, plus the first. Since y doesn't match and I don't know what that is, I'll take a derivative of that whenever it is known. What's the derivative of x squared? That matches. Now again, even though on a test you don't simplify, I need to solve for dy dx. So I move that to the right and that to the right. So here you always have to kind of get a dy dx by itself, which means you're going to have to simplify. Factor a dy dx out. And dy dx would be divide both sides by that parentheses. I thought those were the same for a sec, just by looking at them. There is another way of doing this. I just want to set it up for you. I want to show you there's another way of doing this. If this is really bothering you, and it should bother you a bit until you get the hang of this. Another way of doing this. And what I'm showing you right now, a student showed me this, so you know it's not like my doing. Okay, I don't know what just happened. Let me fix that. So another way of doing this, if you take, so this is the same problem we just did. You could say bring the power down, subtract 1 from the power. So every time I take a derivative of a variable, I pick a d dx of that. So bring the power down, subtract 1 from the power times d dx of the y plus the product rule. Derivative of the first, d dx of the first times the second plus the first times d dx of, actually, a better way even. I'm sorry. That'll take care of business. Bring the power down, subtract 1 from the power, times the derivative of y, plus, here, product rule, derivative of the first, dx, times y, plus x times derivative of y is dy. I have a power function, bring the power down, subtract 1 from the power, times the derivative of that. And derivative of constant is 0. A student showed me this trick. If you want dy dx, just divide all of those by dx. Each of those two terms by dx. In the beginning, that's probably a good thing to do. This will be 2y dy dx plus dx's cancel out. y plus x dy dx plus those cancel out, 2x equals 0. You're at this stage, and you could take that route. I will do the next problem this way as well. So a student showed me this trick, and I showed it to my students back in the days, and they really liked it. In the beginning, until we get the hang of this, so here we are. If we want to take a derivative of this, the product rule. Bring the power down, subtract 1 from the power, dx times y cubed, plus x cubed times, bring the power down, subtract 1 from the power dy, minus the product rule again, derivative of the first, bring the power down, subtract 1 from the power dx times y, plus x squared dy, plus product rule, derivative of the first. Oh, I just realized what I did. Fix the problem. Product rule, derivative of the first is dx times y squared, plus first derivative of y squared is 2y dy. It's one excuse me, extra step. And now, since you want dy dx, divide each of those by dx. The colors are not registering today at all. Divide this by dx, divide this by dx, this by dx, each of those by dx. And the dx's cancel out. You end up with 3x squared y cubed plus 3x cubed y squared dy dx minus 2x y minus x squared dy dx plus y squared plus 2y dy dx equals 0. I'm going to work this right there. So I'll leave everything with a dy dx on one side, factor dy dx out. I'll have 3x cubed y squared minus x squared plus 2y. That would be those three. I would move this to the right, this to the right, and this to the right. And dy dx would simply be negative 3x squared y cubed plus 2xy minus y squared all over the parentheses. And there it is. So it's up to you. You want to use the shortcut, you can. You want to use that ddx until you get the hang of this. Bottom line, you need to get this before we tackle 2.8, which is why I'm doing 2.6 and jumping to 2.9 and leaving 2.8 for next week. Well, derivative of this with respect to x, that will be dy dx equal negative the sign of x plus y times with the product rule. Derivative of x is 1, derivative of y is dy dx. And now to solve for dy dx, I need to distribute. Get all the dy dx's on one side. Before this adds up. And if I factor dy dx out, I'll have a negative sign of x plus y divided by a 1 plus sign of x plus y. So if I factor dy dx out of both of those, out of the first I'll have a 1, and out of the second I'll have a sine. Divide both sides by that, and there it is. I'll tell you what. No need to squish things. There we go. We have plenty of space. So if I factor dy dx out, I'll have 1 plus sine of x plus y equaling negative sine of x plus y. And if I divide by the parentheses, I'll get negative the sine of x plus y divided by 1 plus the sine of x plus y. There it is. If I look at the next problem, same deal. If I look at the next problem, I would take derivative of sine, cosine is negative the sine of y, dy dx, equal product rule. Derivative of the first is a 1 times the second, plus the first times derivative of the second, plus derivative of 5x is 5. Get the dy dx on one side. Factor dy dx out. And dy dx would be y plus 5 divided by negative sine of y minus x. You could factor a negative out of the denominator if you want, but it's the same thing. And a couple more to go. Actually, I have 3 more problems to go. So if I start with the first problem, and I'm trying to match what you do in the homework. So derivative of tangent is secant squared of xy times product rule. Derivative of the first times the second plus the first times derivative of the second. Derivative of 1 is 0. Derivative of cosine is negative the sine of y dy dx. Distribute y secant squared of xy plus x secant squared of xy dy dx equals negative sine of y dy dx. Swap those. X secant squared of xy dy dx plus sine of y dy dx equals negative y secant squared of xy. I'm not liking that way at all. Factor a dy dx out. You know what? Yeah, I should have did that for the other problem. I just need one more line. I can just add a bit of space, and this way I could have had all the room that I wanted. You learn something new every day. Divide by the parentheses, and you have isolated the derivative. There it is. And if I look at the last problem, well, derivative of y cubed is 3y squared dy dx plus product rule. Derivative of the first, 2x times y plus x squared times 2y dy dx equals the product rule. 1 times y plus x times dy dx. So if I move all the dy dx's on one side, everything else on the other side, 3y squared dy dx plus 2x squared y dy dx minus x dy dx equals y minus 2xy squared. Factor a dy dx out. Divide by that parentheses. And there it is. I should have done that. I should have just added extra space for part K. Oh well. Okay, last problem that we have to deal with. Find an equation of the tangent to this curve. Well, y minus y1 equal m into x minus x1. Almost done with the problem. There's x1, there's y1. I need to take a derivative. Derivative of a square root is 1 over twice the square root of x. Derivative of square root of y, 1 over twice the square root of y, dy dx. And here, the 2 I leave out. The product rule, derivative of the first times the second plus the first times derivative of the second. Now I could clean it up, but if x is 1 and y is 1, plug 1 for x, that's 1/2, plug 1 for y. Much easier to deal with numbers. So clear the parentheses out. Actually, if I clear the fractions altogether, LCD is 2. So multiply this by 2, that's a 4. Negative 3 equals 3 dy dx. So dy dx happens to be a negative 3 over 3, which is a negative 1. Put a negative 1 there. There it is. Done deal.